All right, good afternoon, everyone. This is our last hurrah before the final. No tears, please. Finals next Thursday, 12:30, right? 12:30, 30 minutes before we normally meet. It'll go till 3:15. I probably already mentioned this, but you can have a standard sheet of paper, 8.5 by 11, front and back. You can put anything you want on here in terms of formulas, steps, procedures on how to do things. You may not just have worked out problems though, right? And you must turn in that sheet with your work. All right, and then also when you show it to the camera, right, you'll be showing that to the camera when you start your test next week. We do not have class Tuesday, all right? There is no class Tuesday. Right now, I am trying to figure out a time that I can be available this weekend, mostly for my Cal 1 and Cal 2 classes. I'm thinking Saturday, since Sunday is Mother's Day. Most people will be busy. Saturday, I'm looking to maybe have a time slot of about 3 hours or so where I can be available to everyone. I will let you all know. I'm trying to work out my weekend schedule right now. So keep your eyes on your email for that. Yeah. Other than that, in terms of the final, I gave you a review. I said it was part 1. I still think I might give you some more to go off of, but I think I gave you plenty to play with there, right? So see how that goes, and if I'm going to give you a second part to it, I'll do that within the next 48 hours. Questions?
Can you please work out question 14 on the 4.7 homework if you have time?
Yeah, I have time. 4.7.
Yeah, question number 14.
4.7. Question number 14. Yeah. Okay. Yeah. You know what? You got me again, Ash. You got me again. That one is an arctan problem, which we didn't talk about. I'm sorry, I didn't see that one. Did I assign that one?
On 4.7?
Yeah.
Yes, I believe.
I did assign the evens there.
Yep.
Really?
Because this is 4.7,
Yeah,
right? Antiderivative.
Yeah, I did put 14 on here. I told you could go try those now. Yeah, so I shouldn't have given you 14. Because you need the arctangent, the derivative of arctangent, which we didn't do the inverse trig functions. So if it's okay with you, let's hold off on that.
Yeah, of course.
Okay.
Thank you.
Any other questions? Okay, so last time we ended class talking about this idea of trying to find an antiderivative of something using this technique called substitution, right? So I'm going to do an example first, and then maybe we'll look at those homework problems, and then I'm going to do more examples. And I'm going to do examples maybe for the first 20 minutes or so, 30 minutes, and then I'm going to move on to another topic, and then we'll be done. All right, so let's try this. What if we're trying to find the antiderivative of, let's go with x cubed over 1 plus x to the 4th dx. All right, so what that means, right, what we learned last time is that means you want to look at this thing and you want to see if you can find the antiderivative of it. So we start by thinking about, the things that we know, I guess, before we talked about substitution, which is we could find the antiderivative of x to any power. Like we got that. We understand how to do that. There's a formula for it, right? In fact, the formula is 1 over n plus 1, x to the n plus 1 plus some constant so long as n was not equal to -1. And if x was equal to -1, that would be this case, then your answer is natural log of the absolute value of x. I told you start putting the absolute value around that x for the antiderivative. Those are like the things that we knew before substitution. And then other things we knew were things that you should just know from Cal 1, which is things like the antiderivative of cosine of x would be sine of x plus c, or something like the antiderivative of e to the x would be itself, because the derivative of e to the x is e to the x. So these are all things that we would be looking for here, but none of these things work because yes, we do have x to powers, but this is division, so you can't just use this rule, and you also can't split it into two fractions. So that leads us to the next idea, next concept, which is the substitution. So I said with substitution, what you're doing is you're looking for something, right? Something and its derivative. And the derivative needs to be in the numerator and it can't be trapped. So since this is our first example, I hope this is obvious. The entire denominator, if you take the derivative of that, you get 4x cubed. And up top, we have x cubed. We're off by 4, but I told you it's okay if you're off by a constant. So what I'm going to do is I'm going to make a substitution. U is equal to 1 plus x to the 4th power. Then what I'm going to do is I'm going to take the derivative of that with respect to x, and that will be 4x cubed. Then I will multiply both sides by dx to get this expression. And now I see I've got the x cubed in the dx here, which is in my integral, right? In this integral, the x cubed dx is right here. So I'm going to start to manipulate this integral to make it kind of look better for me to work with. I'm going to take the x cubed and slide it to the side next to the dx. That I can do, that's just properties of fractions. Pull this off to the side. And now this thing matches, right? Like it matches almost exactly. This right here is that part in green. I just don't have the 4 over here. I have a 4 over here on the right, but I don't have a 4 there. Give me a second. I restarted my computer because of the storm last night. And so I need to get my pointer back, my highlighted pointer. There we go. So this green matches this green, except that 4 is not over here. So what I'm going to do is I'm going to multiply both sides by 1/4 to get the x cubed dx to match perfectly now, right? Those match. And then I also know that the 1 plus x to the 4th, that matches exactly with this. So I'm going to replace the blue with u, and I'm going to replace the green with 1/4 du. And when I do that, I get a new integral, 1 over u times 4 du, not 4, 1/4 du. And now, because 1/4 is a constant, I can pull it out in front of the integral, because constants, that's the way they behave, right? They'll come for the ride. So I'm just going to bring that constant out front. And then I have 1 over u du. And that I know the antiderivative of, because that falls into this category right here, where if you replace that with u, then that's basically, I'm sorry, u and du, right? Replace u here and u here. That's exactly what I have, right? So the antiderivative of 1 over u du should be 1/4 times the natural log of the absolute value of u plus some constant. So no more, notice I don't have an integral sign anymore, right? The step from here to here is actually me doing the antiderivative, right? Everything up to that was me rewriting the problem in a way that would work for me to take the antiderivative by making a substitution. And then finally, I have to replace u with what u was, and u was 1 plus 1 plus x to the 4th plus c. We're done.
I have a
Question?
question.
Yeah.
Why is it better to take the set 1 plus x to the 4th as u versus just x to the 4th as u?
Just x to the 4th? Okay. Yeah, I can show you why it's better. All right. So let's say we start this problem over, right? And let's say we did 1 plus x to the 4th here, dx. But you said, when you were doing the problem, you said, you know what? I know the derivative x to the 4th is 4x cubed, so I'm off. And I'm going to let u be that, okay? So you let u be x to the 4th instead of 1 plus. Well, you'll still do the same thing. Du, derivative of u with respect to x is 4x cubed, right? You'll multiply both sides by dx. And now you'll play this game where you rewrite this. Slide the x cubed off to the side, right? So everything here is the same so far. You're going to try and match this up with this. So you will still have to multiply both sides by 1/4. Okay. Here's where it'll be different though, because when you go and rewrite the problem now, you're going to replace x to the 4th, right, with u, and you're going to replace the green part with 1/4 du. So let's see what that would give us. We would have 1 over 1 plus u, and then times 1/4 du, right? But you see, you still have a 1 plus down here. So you can pull the 1/4 out. But see, now you can't use the natural log because this is not 1 over u, it's 1 over 1 plus u. Do you see that?
Yes.
Everyone see that? Now, it's okay, you can still get around it, but now you have to make another substitution. The substitution, and this is not as clear because it's almost so clear, it's not clear. That doesn't make sense. Okay, so what I'm going to do is I'm make another substitution. I need to use a different variable. I'm going to let v be equal to 1 plus u. And the reason I'm doing that is because if I take the derivative of v with respect to u, I get 1, right? So if I ask you to take derivative of both sides of this with respect to u, derivative of v with respect to u is dv du, derivative of 1 is 0, derivative of u is 1 with respect to u. And then you say dv equals du. Multiply both sides by du. And now we match again. Du is going to get replaced with that, and the 1 plus u will get replaced with v. So it now becomes 1/4 integral 1 over v, and then du is dv. Do you follow that, Ash?
Yes, I do.
Everyone, yeah. So now we can do the antiderivative of this. The antiderivative is natural log of v, right? Plus a constant.
Yep.
Okay, what's v?
1 plus u.
1 plus u.
Which is x.
And then what's u?
1 plus x to the 4th.
Just x to the 4th, right? So it'll be 1 plus x to the 4th, which is the same answer, right?
Yeah.
But you had to do 2 substitutions. So the idea is that what you want to do is you want to grab, for your choice of u, you want to grab as much as you can without grabbing too much. Okay? It is possible to grab too much. Let me give you a slightly different variation of this problem. Are there any other questions before I move on? How about this? What if I did the same problem, x cubed on top, but on the bottom, I did 1 plus x to the 4th to the 5th dx. So one thing I could do is let that be u, right? In blue, I could let that be u, and the derivative of that's 4x cubed, which is up top. I could do that. I could do 1 plus 4x cubed. That derivative is, I'm sorry, 1 plus geez, 1 plus x to the fourth could be my u, in which case the derivative would still be 4x cubed, right? So there's no difference between me doing that and that, right? No difference in terms of the derivative. Or I could maybe grab everything with the 5, but that's too much. Why is that too much? If I let u be the whole thing, right, to the 5th, then when I take the derivative of that, I have to do chain rule. 5, 1 plus x to the fourth times 4x cubed, right? That's what I would get. And the problem with that is this on the bottom, this is already, look, everything here, that right there, that's your u, right? That's your u. So the only thing left here is the x cubed dx. And look what you have. You have all this crap over here, right? All this stuff is too much. Like that derivative created too much stuff. You've got this, but now you've got this extra stuff that's not part of your integral. Does that make sense? You sure? It's too much. So there's a fine balance that you have to find, like letting you be enough to be efficient, but not so much that you can't do the problem. And that just takes time and practice to get better at what to choose here. Okay, let me give you another one. All right, I'm going to give you another problem to look at. How about this one? How about integral e to the square root of x over the square root of x dx? So remember I told you last class that when it comes to Cal 2, your ability to be good with derivatives has a direct impact on your ability to do antiderivatives and go backwards, right? And when I said that, what I mean is, how much of this can you see in your head already? Like, how much of this can you put a u in your mind right now, take the derivative of that u and see if you see that there without actually having to write it all down? You know what I mean? Like, but if you don't know the derivative of some things, then it's going to be hard for you to do this. So does anyone see what I could try to let u be? You're looking for something, and then its derivative has to be there, and you're willing to be off by a constant.
Square root of x.
Okay, so let's try that. If I were to let u be the square root of x, the derivative of that with respect to x would be 1 over 2 root x, right? We know that, we better know that. Du is 1 over 2 root x dx, right? Multiplying both sides. So the question is, do you see a 1 over 2 root x? But really, you don't have to worry about the 2. If you see a 2, you see a 2. If you don't see a 2, don't worry about it. So do you see a 1 over root x somewhere?
Yeah.
Yeah, it's there. You just have to manipulate this. You have to rewrite this integral as e to the square root of x times 1 over the square root of x dx, right? That's just algebra. That's just me kind of pulling it apart. And so I have a 1 over root x dx, which matches up with this piece right here, with the exception of the 2, right? I have a 2 down here. I don't have a 2 over here. And then also the root x here, that's what my u is going to be. So now I'm starting to think, okay, this integral is going to turn out to be like e to the u, right? E to the u. And then this part over here is just, I've just got to somehow get rid of this 2. So how can I get rid of that 2 over here? What do I do? I don't want
Multiply
this.
both sides by 2.
Yeah, just multiply both sides by 2. All right, so you're just going to multiply the left side by 2 and the right side by 2. This 2 and this 2 cancel. And you have 2 du equals 1 over root x dx, which is precisely what I have right there. So when I rewrite this, I'm going to have e raised to the blue piece, right? But the blue piece is u times, and then the yellow piece is 2 du. The 2 can come out in front. And now I'm just asking you, what's the antiderivative of e to the u? Well, itself, right? The antiderivative of e to the u is e to the u. So this is going to be 2 times e to the u, then plus your constant. And then take that, replace u with the square root of x, and you're done. You can check your work, can't you? Can't you check your answer? Take the derivative of that. If you take derivative of that, you better get this. What do you think?
When did we start using the equal sign versus using the integral sign?
When do we start using the equal sign?
Because whenever you go, but oh, okay.
Yeah, these are equal. I'm sorry. These are all equal, like that equals that equals that equals that equals. The integral sign goes away when you actually do the antiderivative, right? From here to here, we actually took the antiderivative.
Okay.
Yeah, I'm sorry. I should have equals there for each of these. So I want to mention something here. In the original integral, what was our variable that appeared everywhere? What's the variable? X, right? X, it's x here, dx, right? When I made the substitution, do you see that the integral that I have right here, do you see I've converted the entire integral to have just u's in it now? You have to go from x's to u's. You can't have u's and x's together in the integral. It's got to be all x's or all u's. So that's why I had to replace this yellow piece with 2 du. All right, I'm substituting that out. If you don't substitute that out, you're gonna have e to the u, and then you're gonna have x's, and now you're trying to find the antiderivative of something that has 2 different variables in it. We don't do that in this class, right? We don't do that in Cal 2, we do that in Cal 3. So we have to get everything to the same single variable. And then when you get your answer, right, this answer we got here, when we get that answer, your answer cannot be, this red box cannot be your answer, because your answer has u in it. So it's kind of like me asking you, what's your favorite color? And you tell me the number 13, right? Like number 13 isn't a color. U is an X, right? They're not the same animal here, you know? So you've got to get everything back to X, which is why we substitute back what U is, right? Okay, this one's out of the book. This is an interesting one. How about this? Tangent x times natural log of cosine x dx. Oh, this one's tricky. All right. Let's just start like throwing darts at this. If I let u be tangent to x, what's the derivative of tangent x?
Secant squared x.
Secant squared x. Do you see a secant squared x anywhere?
No.
No. So we're probably not going to use tangent for u. Okay. How about cosine of x? What's the derivative of cosine of x?
Negative sine.
Sine. Do you see a negative sign anywhere? No. Right? Well, kind of. I don't know. I mean, tangent is what? Sine over cosine? So there is a sign here, isn't there? There is a sign.
Could you take the derivative of natural log of cosine of x?
Sure, if you want. Do you want to do that? Are you saying you want u to be the natural log of cosine x? We hadn't considered that. We first considered tangent, said, nah, that doesn't look promising. We considered cosine, said, oh, the derivative of that's negative sine, and we don't see it directly, but there is a sine here, right? And then now, Ash, you're saying, can we let u be the whole thing, natural log of cosine? I don't mind doing that if that's what you want. But what's the derivative of natural log of cosine of x? Can you do that in your head? What is it? Just think, just kind of read it out.
1 over cosine x
1 over
times
cosine.
sine times negative sine x.
Times negative sine. 1 over cosine times negative sine, right? That's
negative sine x.
Negative
over
sine x over
cosine.
cosine x. What's negative? What is sine over cosine?
Tangent.
That's tangent. Do you have that there? Yes. Do y'all see that? It's there. So yes, Ash, good. We're going to let u be the natural log of cosine of x. All right. The derivative of that with respect to x is 1 over cosine x times the derivative of the inside, negative sine x. Now I'm going to multiply both sides by dx. And I'm also going to rewrite that as negative tangent x dx. So I'm just putting the negative sign on top of the cosine and just using the fact that sine over cosine is tangent and putting a negative in front. And I'm super happy to see this, right? If I let this thing, and if this whole thing right here is going to be my u, right? That whole thing is going to be replaced with u. Then I need a tangent x dx somewhere, which I have a tangent x dx. But do you all see that I'm off by a negative? That's fine. I'll fix it. I'll multiply both sides by -1. It's a game we're playing here, okay? This is why some students do really good with this, because they like the challenge that this is kind of like a puzzle you have to figure out. It's not mechanical like product rule, quotient rule, chain rule. That's what I said to you last time. It's not just learn the rule, execute the rule. This is think about it, play with it. You're going to make more mistakes than you are going to be successful as you're learning this material. There's a lot of times where you're going to just cross out what you're doing and start over because you use the wrong u and you're not getting anywhere with it. All right. So it's okay to fail as you learn. You just, by the time you get to the test, and you want to be able to not make those mistakes. So it's just practice, 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 practice. The more you do, the better you get. Okay. Any questions up to this point? I am going to rewrite it so that hopefully it's clear to everybody. I'm going to slide the tangent to the other side. Okay. Slide tangent just to the other side of the natural log, just so you can really see that we have isolated the part that's going to be u from the part that's going to be replaced here with, that part in blue is going to get replaced with negative du, right? Negative du. So my new integral is, well, I'm replacing the whole yellow thing, right? Everything in yellow is getting replaced with u. So that's just u times, and then the blue is getting replaced with negative du. I'm going to pull the negative out because it's kind of like a -1. Well, kind of like a -1. It is a -1, but I'm just going to pull it out front. And now look, the new integral is all in terms of u. So do you know what the antiderivative of u is? The antiderivative of u. What's the antiderivative of x?
One half x squared plus c.
1/2, right? So this is where you have to use the power rule. This is like u to the first power, right? Or like x to the first power. The antiderivative of that would be 1/2 x squared. Antiderivative, right? Not derivative, antiderivative. So this should go to negative, I'll put -1 times 1/2 u squared plus c. Or if you like, -1/2. What was u? what was the thing that we're squaring here? U was natural log of cosine x. Natural log of cosine x, oops. Natural log of cosine x squared plus c.
I have a question.
Yep.
Are we not doing the absolute value for the natural log here?
We didn't do the antiderivative of 1 over u. If we did the antiderivative of 1 over u, we would have put natural log of absolute value of u plus c. But we did the antiderivative of just u to the first power, which is 1/2 u squared. The fact that our u was natural log does not mean we need an absolute value. You only have the absolute value if you do the antiderivative of 1 over u. Then you have the absolute value.
Okay.
Okay. So the looks on your faces, I'm not sure if it's because this is the last day and y'all are like, okay, I'm done. I checked out, or if it's like this stuff looks terrifying. I'm not sure what it is. All right, I'm gonna do maybe one more. Okay. And this is not meant to scare you. Okay. I'm all about being honest and open with you. I don't want to paint anything in, as something it is not. Okay. Cal 2 is hard. Okay. It's hard. All right. But people get through it. All right. It's not, I don't want you to go into it defeated, but I want you to have an appropriate respect for it, because you can't just skate through that class. All right. You can't. It's just, I've met very few, maybe 1 or 2 people in my 20-something year career that didn't have to try in Cal 2. It was just somehow they just could do it. All right. Everyone else, even my best students, have to try pretty hard. So let me just show you an example of a substitution problem that will start to make you go, wow, okay, this is not going to be even as clean as I think it's going to be, even if you don't think it's going to be clean. How about this? How about x? And then how about 1 plus x to the 100th power dx? So we know that if we have x to a power, right, and we want to do the antiderivative, we're good, right? If it's x to a power. And we also know that if there's addition and subtraction between a bunch of powers of x, we can handle it. I mean, like, let me go back to last class. Like if we have a bunch of separated terms with addition and subtraction, we can do them separately, and that's no problem. Here, I could, if I wanted to, take 1 plus x and multiply it times itself 100 times, right? And I could do 1 plus x times 1 plus x times 1 plus x 100 times. And if I did that, I get this humongous polynomial, right? I get this massive polynomial. And then what I could do is I could take the x in front and distribute it through. But you would never want to do that, right? Nobody here wants to expand 100 factors of that. Right? You'd be here for like 3 days doing that, and you'd probably make tons of mistakes, right? So there's no way that we can get this into just like x to a power plus x to a power plus x to a power plus x to a power and do them individually, right? No way. But on the other hand, there doesn't appear to be a clean or clear substitution I should make, right? Like, what substitution do I make here? I'm looking for something and its derivative. What are your choices?
What if you grab the 1 plus x to the 100th, but then you broke it down into
You want me to grab the whole thing to the 100th power?
Well, not the whole thing. It would be 1 plus x to the 50th power squared.
Yeah, you could do that. I mean, but I'm not quite sure where you're going with it.
Yeah, I'm not sure either.
Okay, but you know what? What you're doing is exactly what a Cal 2 student has to do. You have to start thinking about things that you can try. All right. I'm terrible with analogies, but it's like, I'm not a baseball player. Okay, but my understanding of baseball is that in order to ever hit a home run, I'm gonna have to like strike out a lot of times. I'm not gonna hit a home run every time. I'm gonna have to swing though. Like if I don't swing, I'm never hitting a home run. So with Cal 2, you have to be willing to take swings at things. All right.
Is the derivative of x 1 or no?
Yeah, the derivative of x is 1. That is correct. Yes.
Can we do that one? Or
Okay, so you just want me to let u be x?
yeah.
Okay, look, let's try. Look, batter up, okay? Batter up. Here we go. If I do this, what's the derivative of u with respect to x? We just said that that was 1, right? And then you multiply both sides by dx and you just get 1 dx.
Mhm.
So everywhere I see
I cannot get it out.
everywhere I see an x, right? I'm going to replace it with u. And the dx is going to be replaced with du. Right? That's what's going to happen. Let's do it. Integral x is u, 1 plus u again to the 100th power, and dx became du. What have you done?
The same thing.
Nothing, right? All you've done is you changed the problem from the variable from the variable x to the variable u. So, David, the reason why I wanted to go down that route, and I'm glad you said that, is because this is a lesson for us. When we're doing substitution, never make this substitution. Okay, never make that substitution, because you're just going to wind up rewriting the problem. And it's going to be u's instead of x's. You're going to gain nothing from this. Okay. But now at least you can eliminate that, right? Like just, okay, I'll never let u be x. Understand?
Yeah.
Okay, good. So we still don't know what to do. So let's go back to the original. Let's try something else. I mean, x didn't work, right? X didn't work. Batter up. Somebody swing.
Can we somehow put the 100 down like we did in logs?
Or like with a log or something?
Yeah. But,
No, unfortunately we can't, because if we make this like equals y and do natural log on both sides, you cannot pass a natural log through the integral.
okay.
Can't do that. But good, but hey, you're trying, right? You're like, what can we do? What can we do, right? So u equals x, no, right? I'm telling you to just say something, okay? We're gonna try it, and if it fails, I'm gonna fail you in the class, okay?
Possible to use the 1 plus x.
1 plus x. Okay, try it, right? 1 plus x. All right, now this doesn't seem very different than what David suggested, right? Because when we take the derivative, right, du dx, you still get 1, don't you? Right? And then you multiply both sides by dx, you get 1 dx. Right? So right now, from all appearances, it doesn't look like this is going to help. It doesn't look like it is. But this is it, okay? This is it. This is right, okay? Let's see why it's right. What I'm going to do is I'm going to replace the 1 plus x with u, right? That's going to get replaced with u. the dx will be replaced with what? Dx is going to get replaced with du, right? The only thing I really don't know what to do with right now is this, right? Like, what do I do with the x though? I mean, I know I know that the 1 plus x is going to be u. I know the dx is going to be du, but what does the x become? Drum roll. Does anyone see what x becomes?
Constant or not?
What? No, not a constant. Give you a hint.
1.
Look at that equation. If
U.
I ask you what x is, what would you tell me?
You're gonna solve it for x by
U
sub-
minus 1.
we're taking one to the other side.
That's right. You're going to subtract 1 on both sides, and you're going to get x is equal to u minus 1. Right? Is that true? If we're saying u is 1 plus x, then that means x is u minus 1. So that means I'm going to replace this x with u minus 1. Okay, now, if I were you and this were my first time doing this, I'd be like, this still doesn't seem like I'm going to gain anything here, all right? But I'm telling you, let's follow this through. It's going to work. Okay, so now what happens here is this becomes integral. All right, x became what? U minus 1. Okay, times. But the blue is what? The blue is u, isn't it? U to the 100th power. And the dx became du. And you look at that for a second and you're like, well, wait a minute, this still sucks, right? Like this still sucks. But it doesn't. Because look at what you've done. In the original problem, in order to figure out what this is, you would have to take 1 plus x to the 100th power, which we would never want to do 100 times. But here, look, you can just multiply this damn thing through. Just multiply it through. What do you get when you multiply that through? U to what power? If you do u times u to the 100th, you get u to the what?
101.
101. Minus, and now u to the 100 times negative 1.
U to the 100.
To the 100th. du. Now, don't you have two terms separated by subtraction? They're both powers of u. You can use the power rule on each one of them individually. Antiderivative time. Ash, were you yawning? I thought that you were like overwhelmed with like surprise, like, oh my God. This
Sorry,
is
sir.
amazing. This is absolutely amazing. No, you were just tired. Okay.
Yeah.
Okay, so the antiderivative of u to the 101st power is 1 over 102 u to the 102. I'm using the power rule, right? I'm adding 1 to the power. I'm dividing through by 1 over that, minus 1 over 101 u to the 101 plus some constant. See, I've taken the antiderivative now, so that's when the plus c comes in. And the last step is for me to replace u with what it was, right? And u was what? 1 plus x. There it is.
I
So-
have a question. Oh,
Yeah.
sorry.
No, go ahead.
How does that du go away again when you take the antiderivative?
I've been waiting for somebody to ask me about this because as long as I've been teaching this, everyone wants to know where the du goes. All right. So the way that I want you to think about this is when you're doing the integral, right? The antiderivative, when you're at this step right here, think of the integral sign as telling you you want to do the antiderivative, right? And du is telling you with respect to what variable. So it's keeping track of your variable. This is the thing you're doing the antiderivative of. So you do the antiderivative, and then we always do a plus c. So it doesn't really go anywhere. It's part of the notation. that we use to tell you to take the antiderivative. So you're focusing all your attention on doing the antiderivative of that. That's where that comes from. The du and the integral sign just go away.
Got
Now, what I will tell you is this: if in your mind you need that du to go somewhere, if you do, just say that it always turns into the plus c, even though that's not at all what's happening. Okay. If that's a way to help you remember plus c, then do it that way. Like, oh, what happens in du? Oh, it becomes the plus c, and then you won't forget the plus c. But that's technically not what's happening. That's pretty cool, huh? I mean, this problem was a substitution problem that didn't look like it was gonna be a substitution problem, and it wound up working, which should kind of scare you a little bit, because that means there's ways to solve problems where it's not obvious. You just have to try something, right? Like, you just have to try something, and it may or may not work. In this case, it did, right? So there's no, again, there's no like clear path on these things. It's not, I wish it was, it's just not. It's just the nature of the beast. Now look, we may as well check our answer. Let's check our answer. Let's take the derivative of this, because that doesn't look like that. It doesn't look like the derivative of this should turn out to be this, right? Up here, doesn't look like it should, but let's do it. So practicing our Cal 1 skills, we're taking derivative of this first. So the 102 comes out, right? 102 comes out, hits that, goes away, which leaves me with a 1 plus x to what power? 101, right? Now chain rule, derivative of what's inside. What's the derivative of what's in here? 1, right? So that's it. I'm done with the derivative there. Minus, now here, the 101 comes out, goes away, and then I'm going to have 1 plus x to the 100th power. And then plus c, right? Plus c. That, sorry, the derivative of that went away. It's 0. So is that the original thing here? Let me bring this down here. Copy this. Is that, or did we get the right answer? Is this? Is that? Doesn't look like it is, does it? Until you do this, you factor out of both of these. What do both of these have in them? A 1 plus x to the 100th power, right? They both have that to the 100th power. Now, if I pull 100 of these out, I'm left with one of them. So I have 1 plus x. I still have one of them there. Then minus, and if I pull all 100 of these out, I'm left with 1, right? Because I'd have to distribute back through here to get these. And now what's inside that bracket really is just 1 plus x minus 1. And the ones cancel, and you get x times 1 plus x to the 100th power, which is exactly what we started with. So there's some good news here, okay? The good news is that in Cal 2, you are going to get the full treatment, you should get the full treatment of substitution, which means that there's going to be some overlap here. Like, you're going to see this again. But if there's something that I could recommend you start to do to prepare yourself for Cal 2, is to look at a section like this section and 4.7, where you're doing antiderivatives with the power rules and stuff. 4.7, 5.5, those two sections in the textbook, if you practice, that'll get you kind of warmed up for the Cal 2 experience, all right? But this is tip of the iceberg right here. What we're doing is tip of the iceberg. We could keep going. We're halfway through class. We could keep going. I think, what do y'all want to do? Do y'all want to do one more, or do you want to move on? Do y'all care?
Can you do one more?
You want to do one more? Well, let's bring up the review. You want to look at the review? I think I put one on the review. Let's see. I think it might be too similar to the one we just did. Yeah, okay. We'll at least talk about this one. Look at number 20, the last problem on the review. Use substitution to find the antiderivative of x to the fourth over x to the fifth plus 1 to the fourth dx. Do y'all see what u should be? What do you think? Hold on, don't tell me. Why don't you send me a chat? Everybody send me a chat of what they think the u should be. I think you can type it into your chat. While you're doing that, I'm going to go refill my very strong drink. Okay, yeah, so for the most part, everyone got this. The u should be just the x to the fifth plus 1. That's it, just that. Let that be your u. The derivative of that is 5x to the fourth, which is up here, but it's off by a constant. Don't grab the whole thing. Don't grab the 4. If you grab the 4 with it, then you're going to have a chain rule derivative, and that's too much. Right? That's just too much. Okay, so I found another one that I like. Another one that illustrates the complexity of this stuff. All right. Hold on. I want to make sure that, yeah, let's try it. This will be the last one. X cubed over the square root of x squared plus 1 dx. Oh, this one is so good. So your instinct here might be, let u be x cubed. Maybe, it could be wrong, but let's just think this through. If u is x cubed, the derivative of that is 3x squared, right? We multiply both sides by dx, you get 3x squared dx. So do you see an x squared anywhere? You do, right? I see an x squared, but that x squared is in the denominator, and it is trapped underneath the square root. That can't happen. You can never choose something where its derivative is trapped, because you've always got to be able to peel that derivative off to the side to replace it. So that ain't gonna work, all right? That ain't gonna work. So let's see, I like this chat, this is good. Why don't you send me a chat of what you think it should be here? Just take a shot at it. Just take a shot. All right, type me up something, send it to me, what you think we should let u be, just to start. Okay, so the the overwhelming majority of you want me to let u be equal to x squared plus 1. Okay, so I'm going to go for it. All right, let's go for it. Let's see if this is right. Du dx is equal to 2x, right? If I multiply both sides by dx, I get 2x dx. So if I follow this method, which a bunch of you want me to do, I'm going to replace the blue part, right? That blue part right there will be replaced with u. All right, so I don't have to think about that anymore. But I have an x cubed dx here, and over here I have an x dx. I don't have an x cubed. So you might be thinking, oh, I'm going to cube both sides. You can't cube both sides, because if you cube both sides, where's my cursor? If you cube both sides of this, you're going to have du cubed, and you can't have a cubed du in the integral. It has to be just du, or 5 times du or 2 times du. It can be any scalar multiple of du, but it can't be du. Can't be algebraically. It can't be square rooted or squared or cubed or anything. It just has to be itself. So it doesn't look like it's going to work. Do y'all agree? It doesn't look like it is until you do this. You realize that you could rewrite it like this. That's tricky, huh? Instead of writing x cubed, I wrote x squared, and I peeled an x off to the side. Now, this yellow part matches this yellow part over here, right? Now I'm off by 2. That's okay. I can remedy that quickly. I can multiply both sides by 1/2. So that means I'm going to be able to replace the yellow, right? The yellow is going to get replaced with 1/2 du. The blue is going to be replaced with u, but we still have to resolve what to do with x squared, because we can't have u's mixed with x's. So anyone have an idea what I can replace x squared with?
U minus 1.
U minus 1. That's right. I can go back to this and solve that for x squared. Just subtract 1 on both sides. That is what the green part will be replaced with. So my integral becomes the green. The green is u minus 1 over, okay, the bottom becomes the square root of the blue, but the blue was u. And then the x dx gets replaced with 1/2 of du. The half's going to come out. And now you look at this and you're like, well, crap, did we get anywhere? Was this worth our effort? Look, I was just following the lead here. I wasn't telling you this was right. Are we going to be able to handle this? Can we handle this or not? How?
You can split that fraction into 2.
That's right.
Because it's the common denominator.
We have a single denominator that's u to the 1/2 on the bottom, right? You have 2 terms in the numerator. You have a single term in the denominator. And so you can split it into 2. So this becomes 1/2 integral. Let me do it slowly. U over u to the 1/2 minus 1 over u to the 1/2 du. And this becomes 1/2. Let's see, integral. If I do u to the first power over u to the 1/2 power, that becomes u to the 1/2, subtracting 1, take away 1/2. And then this, I'm going to bring the u up as a power, as a negative exponent, negative 1/2. So I was able to split it up, have two terms. Each of those are powers of u, so I can apply the power rule, right? No more integral sign. I'm doing the antiderivative now. The 1/2 is going to be in front. I'm going to have to take this u, I'm going to have to add 1 to the half. So 1/2, I add 1, I get 3/2. So 1 over 3/2, u to the 3/2, minus, then I add 1 to negative 1/2, which gives me 1/2. So 1 over 1/2, u to the 1/2, all of that plus c. I can clean this up a little bit. This becomes 2/3 u to the 3/2 minus 2, because when I flip the fraction up, u to the 1/2 plus c. I will distribute half through. 1/3 u to the 3/2 minus half of 2 is 1, so just u to the 1/2 plus c. You understand where the 1/3 came from and why there's no 2 anymore, right? Just distributed that. What is u? I forgot what u was. U was x squared plus 1. So I'm going to replace it, x squared plus 1, x squared plus 1. We're done. Okay, that's it. I could continue and, you know, make your head spin more, but what I would expect on the test would be something like what I showed you there, this. Okay. This one, number 19, we're about to talk about this right now. You have to find the antiderivative of this, so that would be something I would expect. Natural log x over x. So I would just mess with some problems. In 5.5, I gave you problems 1 through 6 to look at, right? I would say, let me write this down, okay? So in 5.5, 1 through 6, they gave you the u substitutions. Let me write down the ones that I think you should look at. 7 is good, 8's good. 11's interesting. 13, 14, 18. 19's good. 20, 22. We'll stop there. In my Cal 2 classes, when we get to this section, right? When we get to this section, my Cal 2 class, the homework assignment for this is 1 through 52, all 52 problems, because there's no way you can go further in Cal 2 if you can't do substitution. So like, it's like a building block, right? You need this because later on, as you progress, we work the problems out. They're really complicated. And then you get down to, you're like, oh, well, that's just substitution from there. You know what I'm saying? Like, oh, we can do that. And so, yeah. All right, I want to talk about one more topic, all right? And this, I think you'll find this a little bit refreshing, all right? It's like, why do antiderivatives, right? Why in the world are we needing to even do this? Why go backwards? So I would like for us to just kind of clear your mind for a moment. And I want you to consider the function f of x equals x. And I want you to think of it on the interval 0 to 4, okay? So I'm going to graph this for us. Everybody here should be comfortable with the idea that this is just the diagonal line. That's what f of x equals x looks like, but I'm only going between 0 and 4. So up here it's 4, right? Go over 4, go up 4, go over 1, go up 1, go over 2, go up 2, right? That's what this looks like. Can you tell me, without doing any calculus, can you tell me, if I drop straight down, can you tell me what the area of that is? Well, it's a triangle, right? So the area of a triangle is 1/2 base times height. Do you know the base? Do you know how long this base is? Sure, it's 4, right? So this is 1/2 times 4 times the height. Do you know how tall it is? 4 also, right? So this is going to be 8, right? And if this was measured in inches, this would be 8 square inches. Or if this was miles, it'd be 8 square miles, right? That's the area of that triangle. Yeah. Okay. Yeah, we're good, right? This is fine. So now I want you to do something else. I want you to tell me what the antiderivative of this function is. What's the antiderivative of x? Antiderivative.
1/2x squared.
1/2x squared, right? 1/2 x squared. That's the antiderivative, plus c, yes?
Okay.
Plus c. All right. Now I want you to do something else. I would like for you to take that antiderivative and I'd like for you to plug into it the right endpoint of the interval we were just talking about. So what would happen if I asked you to plug 4 into this? You would get 1/2 times 4 squared, right? Plus a constant, which is, let's see, 4 squared is 16, half of 16 is 8, right? So you get 8 plus a constant, right? You all okay with that? Next thing I want you to do is I want you to take that antiderivative, and now I want you to plug in the left endpoint. So if you plug in the left endpoint into the antiderivative, you get 1/2 0 squared plus c, right? And 0 squared is 0, just kills all that out. So all you're left with here is c, right? Now, subtract. I want you to take this answer and subtract that answer. So take 8 plus c and subtract from it c, and what do you get? 8, right? Coincidence? No. Okay, not at all. This is what is known as the fundamental theorem of calculus, or what's also referred to as the evaluation theorem. Let me do another example, and then I'll actually give you the theorem. Let's take a different function. F of x equals x squared. And let's look at that on the interval 0, 4. Okay. If I were to graph that, it would look like this. Here's 4, right? This is way up here at 16 because it's x squared now, right? If I were to now ask you to drop straight down and give me the area here, you can no longer use area is 1/2 base times height. You can no longer use it, right? Because this is not a triangle. However, this evaluation theorem still holds, which means if I can find the antiderivative, which I can, the antiderivative of this is 1/3 x cubed plus a constant, right? If I now take that answer and plug in the right endpoint, I get 1/3 4 to the 3rd power plus c. And let me see, what is that? 4 cubed is 64, right? So 64 times a third, that's 64 thirds plus c. And now plug in the left endpoint, 1/3 0 cubed plus c. That's just c. And now subtract the two. 64 thirds plus c, take away c, you get 64 thirds. And that, in fact, is the area underneath that curve. Which means that if you want to find the area under any curve, then all you have to be able to do is find the antiderivative. If you can find the antiderivative, you're in business. Now, this has repercussions like what that area represents will mean something later. Like it could mean a lot of things in different fields. I think I told you all this a couple of weeks ago. So our real thing is, can we find the antiderivatives or not, right? And that's why we spend weeks and weeks in Cal 2 just making sure we know how to find the antiderivative of something. Okay. The evaluation theorem. Let me give it to you. I'm going to copy it and paste it. Okay, the evaluation theorem, the fundamental theorem of calculus. Suppose f is a continuous function defined on a closed interval. So I give you a function, little f, and I tell you, hey, that's a continuous function, all right? And here's a closed interval. Then this is new notation, everyone. Do y'all see that? That's new notation. It's the integral with the f of x dx. We've been doing that, but now we're going to put these two numbers, one on the bottom and one on the top. This is telling you that you are now calculating the area underneath this curve. Okay, so that's the big difference. This and this. These are called limits of integration. So look, what we did all today, what we've done up to this point is I've given you an integral and you've found an antiderivative and it always said plus c, right? And it was just a function. This is different. This is not what we call an indefinite integral. This is what we call a definite integral. And what it gives you is an actual number. And that number represents area. I think I do have notes that say that this is definite integral. No, I don't have. Yeah, the definite integral. Let me copy that so it's here. This right here is known as the definite integral. Think of definite, when it says definite, it means that you have a definite answer for the area. Indefinite means you have some function plus c, a big family of functions. Now, the rest of this notation, I'm going to help you see what this is because this is confusing. So let me just do an example. Let's say I wanted to know, let's do the problem we just did. Let's say we wanted to know the area underneath the curve from 0 to 4 of x dx. Are you all comfortable with the idea that the answer to this should be 8? This was the very first one I showed you with where we could draw a triangle, right? That is the notation I would put down if I was asking you to find me the area underneath x. That's what I would write. So this means area under f of x equals x on the interval 0, 4. Okay, that's the notation for it now. So the first thing that we do is we find the antiderivative, which is 1/2 x squared, right? Plus any constant, right? So since it can be any constant, I'm going to choose the constant 0, which means I'm just going to not add anything to that, right? Because when we were doing this, when I was showing you this a second ago, didn't that constant just cancel? Like in both cases, didn't the plus c, didn't it cancel here? They just went away. So we can use any constant we want. So I'm just going to use the constant 0. And then what we do is we put a bar next to this and we put 0 down here and 4 up here. What this is just an opportunity for me to write the antiderivative down. Okay, it's like, okay, I have found the antiderivative, there it is. And now I still need to do two things. I need to take that antiderivative plug 4 into it, then subtract from that the antiderivative with 0 plugged in. So let me grab that formula here, and hopefully this will make a little more sense now. I don't want to erase that. Let me go here. Okay, so I gave you the original problem, right? Oops. I gave you the original problem. That's this part, right? And then the first thing we did was we found the antiderivative. And then we put a bar and we put those two numbers there, right? That's what that is. And then the next thing we do is we actually plug the right endpoint, right? B is the right endpoint. We plug it in, and then we subtract from that the left endpoint plugged in. So just remember, this is the right endpoint of the interval, and this is the left endpoint. And then when you evaluate that, we already did that, that's 8. That is the evaluation theorem. You don't have to prove that theorem. That theorem is hard to prove. It requires a lot of work to prove that that's true. But this is a big deal. I mean, that's why they call it the fundamental theorem of calculus. It is a fundamental theorem. So let's see here. I've got an interesting one for you. You ready? Do you get the idea here? I'm sure that you've probably wondered this before. No, you haven't. That if you take the sine function, right? Let's say we graph the sine function. Have you ever wondered on this sine function what the area underneath that first little arc of sine is? Have you ever just looked at that and wondered, I wonder what that area is? No, of course you haven't. But do you think we can figure it out? Well, we have to know what the sine function is, right? We have to know the function. This is sine of x. We have to know where we start and where we stop. Well, it starts at 0. Where does the first arc of sine go through the x-axis? Where's that point? What is this?
Pi.
Pi, right? At pi. So this is pi. What do y'all think? Just gut instinct. Do y'all think that this is a nice number, like 4? Or do you think it's some weird decimal or some square root involved? What do you think? Do you think it's nice, or do you think it's weird?
Nice.
You think it's nice? Let's see. So let's set it up. I'm going to do the definite integral. The way I say this is from 0 to pi. Say that again. I'm doing the definite integral from 0 to pi of the function sine x dx. That should give me the area underneath that. Well, in order for me to do this, I need to know the antiderivative of sine, which I happen to know, right? The antiderivative of sine is negative cosine of x, right? Antiderivative, right? Is that right? If I take the derivative, right, cover up the negative. If you take the derivative of cosine x, you get negative sine x. I don't want that. I want positive sine x, so I have to put a negative in front. So I found the antiderivative, and now I'm going to evaluate it from 0 to pi. Okay, so I'm going to have two things, and I'm going to subtract them. What goes in here first? What do I plug in, the 0 or the pi?
0.
No, careful.
No.
It's always the right endpoint first.
Okay.
Okay, so you're going to plug in pi. So negative cosine pi. And then you're going to plug 0 into it. So negative cosine of 0. All right, what is cosine of pi? So go on your unit circle, go to pi. Cosine is the x coordinate. What is cosine of pi?
-1.
-1, right? -1. And then it's already got a negative in front of it. So this is going to be -1 minus, okay, over here, negative, what's cosine of 0?
1.
1. And so you get -1 is 1, minus -1 is +1. You were right. It's a nice number. That's weird. That's weird shit to me. If you ask me, that is weird. Because sine is such a strange curve. And to tell me that that if you take the area underneath it and that you get the number 2, it just seems it shouldn't be that way. But it is. Okay, it is. Would y'all like to try the one on the review? On your own? And then we can talk about it? So here's the deal. I'll give you a little warning on this. For number 19, I want you to find the area underneath that function on the interval 1e. E is just a number, right? You're going to have to find the antiderivative of that. The antiderivative of natural log x over x. That is not something easy that you can just think of. You're actually going to have to do something first. So I'm going to, everyone write the problem down. I'm going to put you on breakout rooms and see if y'all can talk your way through this. When you're done, come back. If y'all aren't back by 2:32, then I'm going to pull everyone back. Everyone got the problem? While you're in your breakout rooms, you could also discuss perhaps if y'all are going to do any sort of study groups or something, that would be kind of cool. 3 to 4 people in each group. All right, there you go. Okay, I think everybody is back now. You'll get it? Find the antiderivative. That was the tricky part. You have to use a substitution, right? So we're trying to go integral from 1 to e of natural log x over x dx. So you may have done this different ways, but here's the way that I would do this. First thing I would do is I would just forget this problem completely, and I would just be like, okay, can I do the just regular antiderivative? Can I just figure out what the antiderivative is to start? Then I'll get back to this. So I'm going to make a u substitution. What was u? What u works here?
Ln x.
Natural log, right? Natural log x. The derivative of that with respect to x is 1 over x dx. I'm sorry, 1 over x, and then we multiply both sides by dx. And then if you rewrite this as natural log x times 1 over x dx, everything matches perfectly. You don't even have to like multiply or divide by a number. Everything is perfect. Natural log x is u. So this is just the integral of u du, which is 1/2 u squared plus c. And this would be 1/2 u, which is natural log of x, squared plus c. That's the antiderivative. So then I come back over here and say, okay, well, I'm going to write that antiderivative down. And then I can do any c plus any c. So I'm going to say plus 0. And I want to evaluate that from 1 to e. So I'm going to plug in two things and subtract. So I plug in e first. Okay, when I plug in e, I get 1/2 natural log of e squared. And then I'm going to plug in 1/2 natural log of 1 squared. The natural log of e is 1. 1 squared is 1. This is just 1/2. Minus natural log of 1 is 0. 0 squared is 0. 0 times 1/2 is 0, so minus 0. So your answer is just 1/2. Make sense? Okay, just to take a look visually at what we just did, we looked at the function natural log of x over x. We only looked at it between 1 and e. Okay, so we focused all of our attention on that graph right there. And what we were able to just determine is that if you were to drop straight down over there and come over here and try and calculate this area, it would be exactly 1/2. Okay. Kind of cool. One more thing. Promise. I just wanted to point one thing out on the previous problem. Remember when I was asking about the sine and I was curious, like, I wonder what that is. And we said the answer was 2. Well, what if I asked you instead to look at the sine function, but instead of doing the first arc, what if I asked you to find the area of both of these? What do you think your answer is going to be?
Double.
Double? So you think it'll be 4? Well, the only thing that changes is that instead of going from 0 to pi, we go from 0 to 2 pi, right? Instead. And then we go sine x dx. We know the antiderivative of that because we just did it a second ago, and we're going to evaluate from 0 to 2 pi. When we plug in 2 pi, we get negative cosine of 2 pi. And when we plug in 0, we get negative cosine of 0. Cosine of 2 pi is 1. So this is negative 1 minus over here, cosine of 0 is also 1, but we have a negative 1 there. So this is -1 plus 1. So the answer is 0. Uh-oh. What does that mean? It means that when you do this, it counts any area that's above the x-axis as positive area and anything below the x-axis as negative area. And so they cancel each other out. It's tricky, and you'll talk about that more in Cal 2, but you would want that to be 4, right? You'd want the area to be 4, but the way that the evaluation theorem works, you have to pay attention to when it dives below the x-axis because it's going to count that as negative. So the easy fix for this is just to go from 0 to pi, get that answer as 2, and then just double it. And just say, oh, then it should be 4. Okay, that's it. We are going to call it, because I'm out of time. The review. Crap, where'd it go? The review, I think, kind of, I mean, this goes back to everything, right? Limits. So I'll just speak to this very quickly. This limit's going to require conjugate, right? Because you've got square roots involved. This one, you just expand out h plus 2 square it, and then you should get good things to happen. When I say use the limit definition to find a derivative, that means you have to go back and use that limit h goes to 0, f of x plus h minus f of x all over h. That's how you have to find the derivative. Yes, I know the derivative is 4x minus 3. I get it. You can use the shortcuts. Great. You can check your answer that way. If I say use the limit definition, I want to see this. Please do not make me have to take 10 points off of a problem because you just used the super shortcut rules when I ask you to use the limit. All right, please pay attention to that. If I don't tell you, if I say, hey, find the derivative, then you can use the rules. But if I tell you use the limit definition, then you have to use the limit definition. Find the equation of the line which is tangent to this. So you basically want to find the equation of tangent line. So you're going to be using that y minus y1 equals m times x minus x1. You just need to know what the slope is because you already have a point. The slope is the derivative of this evaluated at this point. So that derivative you can do however you want because I don't say use the limit definition. Okay, and then when you get to number 5, this is take the derivative. That's a quotient rule, right? Quotient rule. Number 6, find the derivative. Okay, that's chain rule. Find the derivative. Number 7, implicit differentiation. So I'm asking you to find the derivative with respect to x on both sides. Okay, we've talked about volume. This is not optimization. This is a related rate problem. Number 8. If you see a related rate on the final, it will be something very simple like this one. It's not going to be complicated geometry. It's just going to be, do you remember the process? You know, what are you given? What do you want? All that stuff. Okay, number 9, find the derivative. This is also chain rule, but it involves a natural log. So you got to know what the derivative of natural log of something is. But other than that, it's chain rule with product. Number 10 is just, you need to know what the derivative of 4 to something is. So this is derivative of an exponential. And then you'll have product rule. Number 11 is where things get weird because you're trying to find the derivative, but you've got x's in the base and in the exponent, which means you need to bring in a log. Number 12, I recommend you bring a log into this. If you got to go, you got to go. It's ready, 242. These limits are probably L'Hopital. Yeah, they're L'Hopital. The first one's infinity over infinity. You can just go right to L'Hopital. This one is going to be 0 to the 0. So you've got to somehow get that power down. Logs are going to be involved, but it ultimately will be L'Hopital. Absolute max min. So number 15 is finding the max and min on a closed interval. Closed interval. Number 16, increase, decrease, concave up, concave down. Inflection, nice function, right? Nice function. I will try and keep it nice on the final. I won't give you something like the last exam that kind of destroyed everybody. And then let's see. Okay, this 17 is from last class. I give you the second derivative. I give you information about the derivative and the function. I ask you to go backwards and recover what the original function is. And then here, antiderivative, split it up, right? 3 different things, power rule. This one you just did, it required substitution. Last one, substitution. That's it, we're done. So thank you all for a good semester. I had put a little thank you here. Thank you for a great semester. I do appreciate everyone that, participated, cameras on. It was real good to be able to look up and see people. It's good luck on all your other finals. And I, again, will send something out, hopefully Saturday, I will be available. But if not, if you're stuck on something or have a question, do not hesitate to reach out to me via text, call me, you have my cell phone number. So, hopefully you'll get together, study together. I don't know. All right, we'll see you. Have a good one.
Thank you. Have a good night.
Thank you so much.
Thank you.